We're getting into waves now, and the first part of this should be review. I'm hoping that at some point you've learned the basics of waves. And then once we do that, we'll get into sound, Doppler effect, and then some more interesting things going on with waves. But this video is purely the basics of waves, and hopefully most of this is a review. So what the wave model does, it describes the basic properties of waves and emphasizes those aspects of wave behavior common to all waves. In other words, waves do certain things, they all do things the same way. So what this does is just puts all of that under one big model called the wave model. Just to give you a few definitions, a traveling wave, so just think of really any wave, is an organized disturbance that travels with a well-defined wave speed. And a mechanical wave is a wave that involves the motion of the substance through which it moves. We'll deal with both of those. So think of a traveling wave like a light wave or a sound wave. A mechanical wave would be like an ocean wave. And then a medium is something through which a wave moves. So you can't have a wave unless you have a medium for it to move through. And in general, just think of a wave as some kind of disturbance. It's a transfer of energy through a medium. What is a disturbance? It's when a wave passes through a medium, displacing the atoms that make it up from their equilibrium position. And we'll define what equilibrium is with a picture and everything. You have to have a source where the disturbance is created, and then it's going to travel outward at a speed. So in other words, think of an earthquake. You're going to have the epicenter of an earthquake. That's the source of the disturbance, and then you've got your P and S waves from an earthquake traveling outward at some speed. So waves are going to transfer energy through a medium, but the medium itself does not travel. So think of water in the ocean. You've got waves that go through the water, but the water's not actually leaving the ocean. Same thing with an earthquake. Although it does create a lot of destruction, it's not the crust of the earth that's actually moving. It's just getting disturbed by a wave. Okay, two types of waves we're going to deal with. The first is a transverse wave, and this is when the particles are going to move perpendicular to the direction that the wave travels. So waves on a string would be considered transverse waves, and this is just your very classic wave, so this would be a transverse wave. You can very easily see the wave motion, and the way you make a transverse wave, you're going to move perpendicular to the medium. So the medium's this way, you create the disturbance perpendicular to the way that it would travel. The second type of wave is a longitudinal wave, and this is where particles move parallel to the direction in which the wave travels. So this will be very easily seen with a slinky, which we'll see in class. So you'll create a disturbance by pushing the slinky this way, and then it'll compress and spread out, and compress and spread out. So that's a longitudinal wave, and a sound wave would be an example of that. So what these are actually called, they're compressions and rarefactions, and we'll get into all of that when we look more into sound. But longitudinal, it's a little bit harder to draw, but you want to see the scrunching up and the spreading out. Parts of a wave, and we will label this on the diagram that you have in your notes. First is the equilibrium. That's where a wave would be at rest. So if you think of a slinky, and a slinky is just being stretched out along the floor and not moving, that would be its equilibrium position. Hopefully this is review. Crest is the peak or the maximum distance above the equilibrium. Trough is the valley or the maximum distance below the equilibrium. So crest and troughs or peaks and valleys, same exact thing. And then the amplitude is the maximum displacement from the equilibrium position. So your amplitude can be positive or negative depending if you're dealing with a crest or a trough. And all that means is it's above or below the equilibrium. We also have wavelength, and this is the distance spanned in one cycle of the motion. So wavelength is, it's easiest to look at a transverse wave. So wavelength would be from here to here. So think peak to peak, or trough to trough, or if this is the equilibrium, from here it has a crest, a trough, and then goes back to equilibrium. So this would be one wavelength, or this would be one wavelength, or if you're going from trough to trough, that would be one wavelength. It just has to go between two successive points on a wave. So one crest, one trough. The symbol for wavelength, here we are again with our Greek letters, is a lambda. So the symbol is lambda. The units for wavelength, because it's a length, meters, centimeters, etc. So any kind of unit of distance would be the unit of wavelength. So lambda, again, if you're having trouble with that, that's what it looks like. Okay, so let's label the parts of a wave, just so you have those. These right here are all considered crests. The bottom parts would be considered troughs. The center line right here is equilibrium, so this would be the equilibrium position. This distance here, so what I'm doing in purple, so that, all of those are considered the amplitude. And then the last thing we'll look at will be wavelength. So wavelength would go from crest to crest, or from here to here, trough to trough, or I shouldn't have drawn that over there, so let's undo real quick. So crest to crest, let me redraw this. That's one wavelength, trough to trough, one wavelength, here to here would be one wavelength. So those are all wavelength lambda. Okay, so those are the parts of a wave. And you should be able to look at a transverse wave like this and be able to label. Two things that we have seen before a couple of times, period and frequency. So period is the time it takes to complete one cycle. Frequency is the number of cycles per second, or the number of cycles per number of cycles or oscillations per second. So remember, they are inverses of each other. T equals 1 over the frequency, frequency equals 1 over the period. And then I know that we did do this with circular motion, but just to refresh, the unit for period is a second. The unit for frequency is either hertz, 1 over seconds, or you might also see cycles per second. But those are the units for frequency, just the inverse of period. Wave speed, so think of speed, it's the distance over time. Distance for a wave is wavelength, so speed for a wave would be the distance for a wave, which is wavelength, over the time for a wave, which is period. So wave speed equals lambda over t, but because period equals 1 over the frequency, this is also equal to lambda times the frequency. And I believe this is the only formula you have on your formula sheet. I don't remember whether it's this or this, but you have one of these two on there. So just writing what all of these are, F would be frequency, T is period, this is wave speed, and then wavelength. So this is the only equation that you will get for waves. Okay, wave speed only depends on the medium that carries the wave. It's determined by the linear density of the medium, so you don't really need to know the specifics of that, but you do need to know that if the density changes, then the speed will also change. So the medium is what determines the speed of the wave, but things can happen to the medium that would change the speed of the wave. One of those things would be density. The other thing that can change wave speed in the same medium would be tension. If you have more tension, the wave's going to move at a higher speed. So say you have a string and then you increase the tension in the string. Even though the string itself is the same medium, you'll have a different wave speed when the tension increased. And then linear density, if that increases, then your wave speed will decrease, because more density means more inertia, because it doesn't want to move. So the material will respond less rapidly and the wave will move at a lower speed. You should know what will change the speed of a wave in a medium, so linear density or tension. And then finally, two numbers that you should use and probably have stored somewhere for when we use them. Speed of sound in air is 343 meters per second, so that's just a good number to know. And then the speed of light in a vacuum is 3 times 10 to the 8th meters per second. I would store this in your calculator as a lowercase, or you can't really do lowercase. I would store that in your calculator as C. C is just the symbol that's used for the speed of light. So 3 times 10 to the 8th meters per second for the speed of light, 343 meters per second for the speed of sound. Those are relatively constant. The only time they change is if they go into a different medium. So this does say in air. Air is essentially a vacuum for light. So if sound or light move into a different medium, like water, then their speeds will change, but these are what you need to worry about for now. Okay, we'll do one example. During a thunderstorm, you see a flash from a lightning strike. 8 seconds later, you hear a crack of the thunder. How far away did the lightning strike? We're given the time, so it's going to take, just list what we know. We know that the period is 8 seconds. So it's going to take 8 seconds for and this is actually the period of the thunder. So for the thunder sound to reach us. We know that the speed of sound in air is 343 meters per second. And then we know that the speed of light is 3 times 10 to the 8th meters per second. Light travels so quickly, you essentially saw that instantly, so you saw the lightning strike as soon as the thunder had actually cracked. It just took a while to hear the thunder. So what we want to use is the information for the thunder. You know that wave speed equals lambda over t, so lambda times t equals, the speed times the period equals the distance. So 343 meters per second times 8 seconds is going to give us our distance. And that comes out to 2744 meters for lambda. So how far away did the lightning strike? It struck about 2,700 meters away. So it was about 2 kilometers away where that lightning strike, and then we heard the crack of thunder. Very simple equation to use. We'll do some practice in class before we add the more complicated stuff in.